Hey everyone, and welcome to another video here at Whiteboard Doctor. Thanks for joining us today. Quick disclaimer before we move on. None of these videos are intended to be acted upon as medical advice. Please pause the video here and read the disclaimer in its entirety before moving on. Channel plug. Here at Whiteboard Doctor, our mission is to bring you interesting, relevant, and understandable medical education for all types of lifelong learners, trainees, and practitioners. If you want to follow along, we do have a lovely subscribe button in the bottom right-hand corner of all the videos. Don't forget to hit that like button. And lastly, if you'd like to support us outside of viewing our videos, we have several ways in which you can do that, linked in the video description and pinned comment. Stay well, keep learning, and back to the video. Alright, and welcome back to another video here. We are post-overnight sipping on some espresso and thought we'd dive into, acid-base disorders, video number 4 in the series. And today we're going to be talking about anion gaps. So for those of you just coming across this video, we put out a series on acid-base disorders. If you're looking for kind of a comprehensive view or understanding, we'd recommend going to this video's comment and starting at video 1 and going through the videos in series. If you're just here because you want a refresher on anion gaps, you could start here, but otherwise this might be confusing because each video kind of builds on the previous videos. Alright, otherwise we're going to dive in today everything you need to know about anion gaps. So the first principle here is that plasma, or blood plasma, is always net neutral, just about net neutral, meaning that the positively charged particles balance out the negatively charged particles. There's the same amount of each of them. And these positively charged particles we refer to as cations, and the negatively charged particles we refer to as anions. And the concentration, in brackets, concentration of these is about the same, to the point where they cancel each other out, and we end up with a net neutral substance. And that substance is our plasma or our blood. Well, this can be helpful when we talk about acid-base disorders, particularly when we're talking about metabolic acidosis. All right? Anytime you have a metabolic acidosis, you want to know, is this an anion gap metabolic acidosis, an AGMA, or a non-anion gap metabolic acidosis, or a NAGMA? All right, because this will hone in on the differential diagnosis for the cause of that acidosis. What is causing it will be related to whether it produces an anion gap, such as an AGMA, or a non-anion gap. All right. It's not helpful for metabolic alkalosis. It's not helpful for respiratory acidosis or alkalosis. It's really just helpful for metabolic acidosis. So when we look at the anion gap, what we're actually talking about is a lab calculation. All right, the anion gap is often reported on a basic metabolic panel, a BMP, but that's just the lab calculating it. It's not a direct measurement. And what that calculation is it's a look at what are the primary measured cations and anions in the body. And we have them written out here, right? So the anion gap's the difference between, well, we'll get into this, is the difference between the unmeasured cations and anions. But to understand that, we have to know what the normal measured cations and anions are. So the measured cations and anions are primarily sodium, Na sodium, and potassium, which are cations. They're positively charged. And sodium is above and away the biggest contributor. The two measured anions are bicarbonate, HCO3 bicarbonate, negatively charged, and chloride, negatively charged. So when an anion gap is calculated, you are essentially looking at the difference between these two main measured cations and these two main measured anions. And the difference between them is going to be the difference in the unmeasured cations and unmeasured anions. Does that make sense? Right? Because we know that plasma is always net neutral, and we know that there's a lot of unmeasured cations and unmeasured anions. Things like phosphate, things like sulfate, things like calcium, right? So phosphate's negative, negative, calcium's positive. Even negative and positively charged proteins like albumin that's negatively charged. All these are unmeasured, right? And you can measure them in, fancy science experiments, but we don't measure them kind of traditionally, daily in the hospital, with some exceptions, calcium, phosphate, all those kinds of things, albumin we sometimes do. But nonetheless, the anion gap is just a calculation. The lab isn't doing some fancy thing looking at all these unmeasured ones. The lab is literally taking the sodium and potassium and then subtracting the bicarbonate and chloride. We'll get into this a little bit more because they don't always look at the potassium. So to understand this, I think we need to go down to the equation and then we'll circle back up. So the equation for an anion gap, an AG and anion gap, and this is what the lab's doing, is sodium, right, cation positively charged, plus potassium, cation positively charged, both on your basic metabolic panel, your BMP, minus the chloride, negatively charged, plus the bicarbonate, negatively charged. All right. The normal value is 12 to 16. So what that is saying is that this equation leaves, 12 to 16 positively charged particles greater, positively charged cations greater than, the negative anions, right? But plasma's net neutral. So what it's essentially saying is something is going on at the body where this equation is always going to leave more positive than negative. Quick before we dive into the details of that to further tease it out. Most places kind of ignore the potassium because potassium only contributes very little, right? There's all this sodium and then there's a small amount of potassium. So the equation most labs use is this one, which is just sodium minus chloride plus bicarb, and the normal is 8 to 12. All right, so let's scoot over now and kind of tease out what that means. Well, we know that there are a number of these unmeasured cations and unmeasured anions. And the anion gap is just looking at the difference between, right, sodium, positively charged, and then bicarbonate, negatively charged, and chloride, negatively charged. And the normal is 8 to 12. So if you just look at these, you always will have, 8 to 12 cationic particles more than the anions. And this is normal, right? Because what the equation isn't taking into account, right, is all these unmeasured cations and unmeasured anions. This isn't to say that the blood is always positive 8 to 12. It just is saying that when you only look at these three, you are missing a number of negatively charged anions that would neutralize this and cancel this out. So this is a non-anion gap. This is normal, all right, because you have all these unmeasured anions. A big one is actually albumin, a protein that floats around. We all have a bunch of albumin that's very negatively charged, right? But there's all these other negatively charged particles that are canceling out the positive cations that this equation implies are always floating around to make sure that you stay net neutral, all right? So what we do when we look at anion gap is non-anion gap is we're essentially using this imperfect equation to tell us something about the state of the cations and anions. How does this relate to acid base? Well, these we talked about in the beginning videos, right? You have hydrogen ions, which are positive, and these are acidic, and you have bicarbonate ions, which are negatively charged, and these are basic, right? But for the sake of this equation, it's easier to think about kind of the positive acidic molecules. So acids are cations, are positively charged. So if we have a high anion gap, it is implying that there has been a change in the amount of acidic compounds in the blood because acids are positive. So if we increase the amount of positive particles, meaning there's more acid around, and you leave the amount of negative particles, what's going to happen in the body is that you're going to have bicarbonate, right, a base, come in here, neutralize these acid particles, so you're going to have less bicarbonate, If you have less bicarbonate, this equation, sodium minus chloride, right, plus bicarbonate, your bicarbonate has gone down, so this is going to equal a higher anion gap. And that tells you something, whereas the body compensates for these changes to keep the blood net neutral. Things to keep in mind, and again, we're going to tease that out more below, but when we're doing this equation, things to keep in mind, we got a little ahead of ourselves, is that you have to take albumin into account when doing the anion gap equation. It's one of the few things that you really need to take into account to give you an accurate number, because if you have a low albumin, as we talked about, albumin, ALB, is very negatively charged. Right? It's covered in negative charged anions. So if we don't take albumin into account, you will have a falsely low anion gap. Because the equations, when they did the experiments to look at what was normal, they looked at it in patients who had a normal albumin. So again, if we're doing the anion gap calculations, and it's positive minus negative, and the normal is assumed to have a normal albumin, but your albumin is low, meaning you have a big decrease in the number of anions, right, the number of negative particles, then what you're going to actually see is that there is something going on, but you're just missing it because you didn't take into account albumin. If we think about that kind of in drawing form, if a normal anion gap assumes the albumin concentration is normal, and you have a normal anion gap but a low albumin, what's actually going on is something has taken the place of albumin, right? So let's say we have a normal anion gap, 4 positives, we'll say kind of 3 negatives, just for the sake of this drawing, to make a normal anion gap of about 8 to 12. But that is with all this albumin that's negative floating around, right? Well, if it's 8 to 12, but you have low albumin, so you only have 1 albumin floating around, what that is telling you is that you have another molecule present that is compensating for that low albumin, right? So essentially, there's something else here that is compensating for that albumin not being around, that is making the anion gap look normal even though it is not. So you always have to correct for low albumin. The correction equation is this: sodium minus chloride minus bicarb plus 2.5 times 4 minus albumin. 4 is the normal albumin concentration. So it's essentially the anion gap equation, but then you just put a little addendum here, 2.5 times 4 minus the albumin. So if the albumin is 2, normal albumin is 4, 2.5 times 2, or times 4 minus 2, which equals 2 times 2.5, which is 5 total. You'd add that onto the anion gap. So if we got an anion gap of, let's say, 11, and we were saying, oh, the anion gap's normal, well, you got to correct for albumin. If you have hypoalbuminemia, 11 plus 5 is 16. And this is actually an anion gap, meaning that there is something going on in the blood that we're going to talk more about, creating a higher anion gap than would be measured otherwise. So always take into account hypoalbuminemia. Let's get into what exactly could be going on and how high versus normal anion gap helps us. Well, a high anion gap, or sometimes we just call it an anion gap, metabolic acidosis, means that there are unmeasured acids floating around in the blood. We're going to get into this, but first we want to say, so we can kind of clump both, a normal anion gap means that you're just losing bicarbonate, not loosing, too many O's, losing bicarbonate. But you don't have any extra acidic compounds floating around, you're just losing bicarbonate. So what exactly does this mean? Well, two things. One, acids, as we talked about, not to be an old drum, are positively charged, right? Hydrogen ions are acids. So something like lactate, lactic acid. Patients in septic shock sometimes develop a lactic acid anion gap metabolic acidosis. Well, lactate is a molecule, and this isn't its actual structure, right? But it has all these OH, all these kind of hydrogen ion groups going on, all right, to think about it that way. So do keto acids, someone in diabetic ketoacidosis. So what you can think of it as is these acidic compounds are giving the body all this extra hydrogen ions. So what has to happen for the body to try to compensate? Well, you're going to have all this bicarbonate coming over here to try to neutralize that acid. So what's going to happen is you're going to get a decrease in bicarbonate. So then when you do your equation for anion gap equals sodium hasn't changed, minus chloride hasn't changed, plus the bicarbonate. Well, the bicarbonate is much lower now because all this bicarbonate has tried to neutralize this new acid floating around, and thus the anion gap is going to be high because the equation being used has less bicarbonate present. This is in contrast to, actually we'll just leave this up and we'll scroll to the right. This is in contrast to a non-anion gap. So you have, in an anion gap, you have extra acid, and this will be helpful to think about when we talk about kind of the differential diagnosis of anion gaps. So you have extra acid, right? And this is an anion gap metabolic acidosis, an AGMA. A non-anion gap, ooh, that's very lagged, apologies. A non-anion gap metabolic acidosis, or a NAGMA, does not have extra acid. You're just losing bicarbonate, which is a base. All right. Something that happens, though, when you lose bicarbonate is you actually increase your chloride. Your body does this while you're losing your bicarbonate. And what happens here is if we look at the equation for anion gap, right? Anion gap equals sodium unchanged minus chloride plus bicarb. So your bicarb you're losing with a non-anion gap, but when you just straight lose bicarb, it's not that the bicarb is trying to neutralize acids, you're just losing it. And we'll get into some of the ways you can lose it. Your chloride auto-regulates and increases, which makes this anion gap normal because the amount of chloride increased is equal to the amount of bicarb lost. So do you kind of see the two different pathophysiologies that are going on here? In an anion gap, you have the production of an extra acid. Lactate, keto acid, formic acid. We'll go through these things. Whereas in a non-anion gap, there's no extra acid being produced. You're just losing bicarb for a reason. And if you just lose bicarb, your chloride automatically increases to make this kind of a net neutral, bicarb down, chloride up, which makes the anion gap stay normal. All right. So what does this mean? How does it help? Well, it helps us in terms of deciding what is causing the metabolic acidosis. So we got these from this Understanding Acid-Base Disorders. It'll be linked in the video description. Definitely check it out. So a high anion gap metabolic acidosis, or a HAGMA, this is sometimes just called actually an AGMA. It's not necessarily a HAGMA. AGMA just stands for anion gap metabolic acidosis. Apologies, we don't know why this is lagging so much. These, right, we talked about, are from the production of an extra acid, right? Because as we said, the extra acid consumes bicarbonate so that there's less bicarbonate in that equation, right? Sodium, as we talked about, we're just going to do repetition here. Sodium, anion gap equals sodium minus chloride plus bicarb. So the acid being the new acid, the extra acid, consumes bicarb, and then this leads to a higher anion gap. So they all have unmeasured acids. These are some mnemonics people use: GOLDMARK, Carmel, MUDPILES, Kussmail. But the similar thing here to remember is all of them have extra unmeasured acids being produced, right? So G is glycols, O is oxaloproline, lactate, methanol, which goes to formic acid, salicylates or aspirin, renal failure, keto acids, et cetera, et cetera. And this is kind of just all similar things, but they all produced unmeasured acids. And those unmeasured acids consume bicarb, which makes your anion gap that you're calculating, because it's a calculation, it's not directly measured, it's a calculation, it makes your anion gap higher. All right? Whereas a non-anion gap, a NAGMA, as we talked about, so this is non-anion gap, you are just losing bicarb. You're not creating an extra acid. This is like GI losses of bicarbonate. You know, if you have a lot of GI losses. Renal tubular acidosis, this is where you just don't absorb bicarb. All right. Treatment with a carbonic anhydrase, which excretes bicarb. Excessive administration of normal saline, this one actually just increases your chlorine because normal saline is NaCl. So you see the difference here? The non-anion gap ones, you're not having this extra acid being produced. You're just losing bicarbonate. And what we talked about, right? Again, repetition, anion gap equals sodium minus chloride plus bicarb. And if you just lose bicarb, your body automatically holds on to more chloride. So this is net neutral and it ends up with a normal anion gap because these cancel out. Hopefully that makes sense. We know that there's a lot here between kind of pathophysiology and then understanding how to apply the anion gap and non-anion gap, but hopefully that makes sense. This is something that we use almost daily in the ICU. It's in the emergency department on the general floors. Something that's really important to get a good grasp on. And in our mind, it's easiest to get a good grasp on it if you kind of understand the physiology behind it. Understand that it's just an equation being used, and that equation is imperfect, and we kind of use its imperfections to our advantage, right? If there's more bicarbonate being consumed, so the anion gap is higher, that tells us something. Whereas if it's just bicarbonate being lost, then the chloride automatically increases, so the anion gap's still normal, that tells us something as well. All right, so let us know what thoughts, comments, questions you have down below. Definitely check out the acid-base series. Honestly, especially if this was maybe confusing, go back to those first videos that we put out because it'll give you a better guide into this one. So we're all on the same page with terminology and definitions and all that jazz. If you've watched all the videos, watch this one, you have a good grasp on them, move on to the next videos. We're almost to the end of the series to have that good grasp on acid-base disorders. Nonetheless, we appreciate y'all. Subscribe, hit the bell button, check out our other content. Stay well, keep learning, and we'll see y'all next time.